let's start this video with the challenge problem from the last video. So read it, take a look at the answers, and take your best shot at it. Alright, so immediately we can cross out A, because if the net force were directed towards the center of the circle, then the box would also be following the same path as the car. And D does not make sense in the context of the situation. Alright, so hopefully you said the answer is B, because currently there's a couple of things that could be going on. The most likely being that there's not a large enough coefficient of static friction to keep the box in place. Alright, in this video we're going to be covering period and frequency. So period is denoted by a capital T and basically tells you how long it takes an object to return to its initial position. So for example, in our cases we're dealing with circular motion problems. So say we had an object traveling in circular motion, and just pick a point maybe here, and the period would be, if the object started at that point, how long will it take until it gets back to that point? Or you can maybe have it start here, here, here. It doesn't really matter. What your timing is how long until the object returns back to that point. And then frequency is denoted by a lowercase f, and that is 1 over the period. So you could say period equals 1 over frequency. Frequency would be, you have an object traveling in its circular motion, and the frequency would be how far does it go in 1 second. Frequency is denoted in units of hertz. So let's get some more solid equations here. So using our circle analogy, we can start out with saying distance equals velocity times time. Time is going to be our period, which is going to equal distance divided by velocity. The distance the object is traveling is the circumference of the circle. So we've got 2 pi r over v. Frequency is just the inverse of period, so it would be v over 2 pi r, and the period is measured in seconds. Alright, here is our first practice problem. We've got an object in uniform circular motion with a radius of r and a period t. We want to find the magnitude of acceleration. So, hopefully you're thinking of centripetal acceleration, which equals v squared over r. Because the object is in uniform circular motion, there is no linear acceleration. And we know then that velocity is distance over time, and that would be squared divided by r. We know distance is 2 pi r. Our time is t because it travels 2 pi r distance in time of its period. Squared divided by r. We can say that is 4 pi squared r squared divided by t times 1 over r. So then our acceleration is going to be 4 pi squared r divided by the period. You can see that's a pretty painless problem, but it does have a lot of substitutions. Here we have a sock in a washing machine that has a radius of 1/4 of a meter and spinning at 2.5 revolutions per second, and we want to know the acceleration of a sock at the outer edge of the washing machine. So that's just telling us that we're going to use the full radius. So hopefully you're thinking in terms of centripetal acceleration because we are in circular motion. So we'll have a sub c equals v squared divided by r. We know that velocity is just distance divided by time. So we'll have d divided by t squared divided by r. And what I'm trying to do is get this equation in terms of variables and numbers that we already have. So that distance is going to be the circumference of the circular washing machine. So 2 pi r divided by, we're going to make time our period, squared divided by r. So we can expand and simplify that, and we'll get 4 pi squared r divided by a period. So you can put in your numbers, but notice here that we have a period, and here we're saying revolutions per second. That is how many revolutions the washing machine makes in 1 second. So this is going to be 4 pi squared radius times frequency, because we are given the frequency. So plug in numbers to get 4 pi squared times 1/4, and those should be squared, times 2.5 squared, and you will get about 62 meters per second squared. So that is the centripetal acceleration of a sock at the outer edge of this particular washing machine. Here is the last practice problem for this video. So we have a force of so many newtons applied to an object moving in a horizontal circle at a constant speed with the same force and a smaller radius. What's going to happen to the speed and period of the object? Alright, so let's start with our equation for centripetal force, which equals mv squared over r, and then we can rearrange it to get that v squared equals r times that force y divided by m. So this is a direct relationship between speed and radius, right? So if the radius is going to decrease, then the speed will also decrease. So that rules out A and C. Now we just need to know what happens to the period. Well, we know that speed equals distance divided by time, and that distance will be 2 pi r divided by the time t for the period, and then we can see that period will equal 2 pi r divided by that speed. But we already have an equation for speed if we take the square root of both sides. So we'll have then that v equals the square root of ry divided by m. So we can substitute that in. So I'm going to do it as 2 pi r times the square root of m divided by square root of r times our force y. This is r to the 1. That square root down there is r to the 1/2. So moving this over there, we can have t equals 2 pi square root of rm divided by the square root of y. So from that, we see there's also a more direct relationship, or I should say proportional relationship between the period and the radius. If the radius is going down, then so will the period. So that makes B the correct option. that's it for this video, and here is the challenge problem for the next video. The solution will be on my Instagram page about 24 hours after the release of this video. You can find the link in the description, or you can watch the video solution at the beginning of the next video.